Calculus. In this video we're going to be talking about the graphs of functions and relations. Our IKen statements for this video: I can estimate the value of a function from its graph. I can find the domain and range of a function from its graph. I can find the y-intercepts of a function from its graph and algebraically. I can find the x-intercepts of a function, also known as the zeros, from its graph and algebraically. And finally, I can describe the symmetry of a relation from its graph and algebraically. Now, when we talk about symmetry, you'll also hear labels of even and odd. Our outline for this video: we're going to take a look at estimating the value of a function from its graph. We're going to talk about how to find the domain and range of a function or relation from a graph. Then we'll take a look at finding the x and y intercepts, both from the graph and algebraically. We'll talk about what the symmetry of a graph is, and we'll talk about how to find the symmetry algebraically. Now, let's talk about estimating the value of a function from a graph. So here I have a graph actually made from my Inspire. Don't really worry about what the function is that I use, because we want to use the graph to find out what f of 10 is. That is, what value do we get out of the function when we plug 10 in. And we also want to find out when does this function equal 30. So a little bit of description about the window of this graph. It goes from -1 to 20 in the x direction. It goes from -1 all the way up to 42 up there at the top in the y direction. So in order to find out what f of 10 is, what I need to do is go over to 10 on the x-axis. I have that marked with the red dotted line. I go up to the graph, wherever that curve is at 10, and then I go over to the y-axis and I read off that value. So basically, how high do I have to go at 10 to reach the function? And it turns out that if you count by twos, because that's the way this graph is laid out, f of 10 is equal to 32. Now let's try to answer the question, what's the x value when my function is equal to 30? So in this case, I have to start at the y-axis. So I go find 30 on my y-axis. I go over to find out my x-axis. Now you'll notice this green line actually goes through, the horizontal green line goes through the graph 2 spots. One right after 0. So I'm going to say that x is about 0. And then we see 30 again when that graph comes back up to 30. It's at x equals 9. So when does this function have a value of 30? Well, it has a value of 30 at about 0 and 9. Now let's talk about the domain and range of a function a little bit. So again, I turned to my Inspire, I created a graph, and I altered it a little bit. So there's 3 important features I want to point out on this. I had a hard time doing this on the Inspire, so I went in and I just edited the picture. So the first thing I want to point out are these 3 weird features of this graph. So these are the things that I kind of edited in my image. The first one, this dot at the left end of the graph, it's a closed dot. So that's very important when we're talking about our domain and range. That means that we include that point. Okay, that point is absolutely part of our function. We have a hole here. Now that means that there's no value defined here. There's actually a hole in the graph. So it's kind of the exact opposite of a closed dot. An open dot means that there is a discontinuity in the graph. There's a hole there. And the last feature is this arrow. This arrow, I'm trying to be very specific and tell you that this function goes up and to the right forever. Okay, so this function does not stop. This graph does not stop. So what does all of this mean in terms of our domain? Well, when you're talking about the domain, you're talking about the numbers that go into the function, the x values. So you look for your farthest to the left x value. Now that happens to be that closed dot. So it says specifically, include this endpoint. So it should absolutely start at -2, and it should include -2. And then you go all the way to the right. How far does this graph go to the right? Well, because of that arrow, that means that it goes up and to the right forever. So it goes all the way to infinity in the x direction. But that hole means something. So I say x is greater than or equal to negative 2. Because of that closed dot, I put that or equal to. But then I have to come in and say that because of that hole, and I'm estimating that hole is at about negative 0.8. So I say x is greater than or equal to negative 2. X does not equal negative 0.8. Now there's a couple different ways I could do that. I can actually do it in 2 intervals, but I like this way because it's just a hole. It's just one little gap there. So go ahead and just say that x is greater than or equal to negative 2, but x cannot equal negative 0.8. Now our range for this one, now I have to stop and think about the y direction. And what's the lowest that it goes? Now I'm going to have to estimate for this one. Now the hole, as we start at that lowest point and we go up, yes, there's a hole at, maybe 1.5, 1.6 in the y value. But if you follow, the graph goes down again, and that's okay. It comes back up. But that y value at about 1.5, 1.6 is covered on that right part of the graph. So that hole isn't as big of a deal in the range. So I just say that y is greater than or equal to, again, because that closed dot, I get that or equal to. And again, I'm estimating about negative 4.4 as that minimum value. It goes up, there's a hole, that's okay, it goes back down, it goes up. It kind of like fills in that y value that was missing from that hole, and then it continues to go on up forever. Now, what about something like this? This is actually a circle. Okay, I actually had to create this with 2 different equations in my Inspire because it's not a function. Well, that's okay. We can still talk about the domain and range even when it's not a function. We're just talking about a relation now. We still talk about the domain being the x values and the range being the y values. So I created these 2 curves to make it look like one continuous circle. So our domain, what is our absolute lowest x value? And then what is our absolute highest x value? And then the same thing with the y. What is our absolute lowest y? What's our absolute lowest x? And with this one, because it's centered on the origin, because it's got a radius of 5, our domain and range are both starting at negative 5, ending at positive 5, and it's continuous from left to right, from bottom to top. So they have almost identical domains and range. The only difference is the letter that's inside our set builder notation. Now let's talk about finding y-intercepts from a graph. So here I have another graph made on the Inspire. Here you can see the function f of x is equal to x squared plus 5x plus 6. And what we're looking for is where does the graph go through the y-axis. So I've kind of circled it here, and we would say that our y-intercept is 1, 2, 3, 4, 5. It's at 6. So we just look at our graph, where does it cross the y-axis? Now, if we're trying to find that algebraically, to find y-intercepts, and actually there's only one if it's a function. If there was more than one y-intercept, it would not be a function, wouldn't pass the vertical line test. But if we're looking for y-intercepts, what we do is we plug in 0 for x. Plug in that 0 for x and simplify, and you'll find your y-intercept. So again, my y-intercept is 6. Now if I take a look at that graph again, I'm interested in finding the x-intercepts. I've got 2 of them down there at the bottom. Looks like one of them is at negative 1, 2, 3, 4. So negative 4 and negative 6. So how do I find that algebraically? Well, in order to find the x-intercepts of a function, or a relation for that matter, we set the equation equal to 0. Now, this is probably the harder of the 2. We can plug in 0 very, very easily. Usually it just means that all the terms go away except for the constant. But when we set it equal to 0, now we're going to have to do some algebra, oh no, to find out what x equals. So in this case, we might try factoring this trinomial. We might try the quadratic formula. This would be a great chance to use that quadratic formula that we learned how to type into our TI Inspire. But we've got to do something to solve for x now, and this is definitely the harder of the two cases. We're going to have to use some different algebra based on what our function is. Now let's talk about the symmetry of a graph. So there's three types of symmetry. There's what we describe as symmetry over the y-axis. So when we say that a function is symmetric over the y-axis, we actually refer to that as an even function. There's symmetry over the x-axis, so that means that we can't even have a function. If it's symmetric over the x-axis, it's not going to pass the vertical line test. So we're limited to only relations with those, but that's okay. And we can have symmetry over the origin. Now, if it's a function and it's symmetric over the origin, that's what we refer to as an odd function. You know, if you want to know why is it even, why is it odd, go ahead and ask me in class. I'll tell you why it's called an even function, why it's called an odd function. But just remember that even functions are symmetric over the y-axis, and odd functions are symmetric over the origin. So let's take a look at what each of these look like. Here is a graph that is symmetric over the y-axis. Now it's an even function again, that's what we call it. And really what that means is for every point on the right side, let's say this point right down here at y equals -3, there's a mirror image over on the left side. So symmetric over the y-axis, for every point on the left, there's a point on the right, and vice versa. For every point on the right, there's a point on the left. It looks like a mirror image. It looks very symmetrical. Here's a graph that is symmetric over the x-axis. Now again, this is not a function. This doesn't pass the vertical line test, but since it's symmetric over the x-axis, that means that there is, for every point above the x-axis, there is a mirror image below the x-axis, same distance below the x-axis as the point was above. So this is symmetry over the x-axis. Again, not a function, it's a relation, but we can still talk about this type of symmetry. Here is a graph that is symmetric over the origin. Now again, this is what we call an odd function. So let's take a look at what this means to be symmetric over the origin. If we go find a point, let's take this point right here at y equals -2. So that's maybe at the point 2.5 comma -2. If we go over to -2.5, we see its symmetric partner. So however far right and down, we see the same thing left and up. So this is what we refer to as symmetry over the origin. We also call it an odd function. Now let's talk about how do we find this symmetry algebraically. Now this is going to look really weird. It makes a lot more sense once you try a couple of this. This is how we test for symmetry over the y-axis to determine if a relation is symmetric over the y-axis. We take the function, usually we're working with functions, we take the function f of x, we plug negative in with all of the x's, and if all of those negatives go away, then we say that it's an even function, that it's symmetric over the y-axis. Now you're probably thinking, what in the world do you mean the negatives go away? Well, let's take a look at the example. This is actually the function that we looked at, that W shape. F of x equals x to the fourth minus 6x squared. If I plug a negative in with that x, f of -x, that even power of 4 basically throws that negative away. That even power of 2 basically throws that negative away. So those negatives are not saved, and we say that this function is equal to our original. So it's actually, even after I plug those negatives in, it's just equal to what it originally was. So this is our test for algebraically determining if it's symmetric over the y-axis. To test if it's symmetric over the x-axis, we're going to plug a negative in with the y. Okay, I know it sounds a little bit weird, but testing for symmetry over the y-axis, we plug a negative in with the x. If we're testing for symmetry over the x-axis, we plug a negative in for the y. Again, what we're looking for is like squares that are going to not preserve that negative. That negative is going to go away because negative y squared is just y squared. That negative is going to get thrown out, and we're back to our original relation. Notice I didn't say function, I said relation. Functions cannot be symmetric over the y-axis. Excuse me, I should say x-axis right here. So x-axis right there. I thought I changed that. Okay, so what about symmetry over the origin? How can a function be symmetric over the origin? Well, we still plug negative in with the x. But in this case, that negative can move out front, and we say that it's equal to negative f of x. So we look for functions where that negative doesn't get canceled out, so that inverse function that we saw earlier was f of x equals 5 over x. If we plug a negative in with that x, we see that negative plugged in down here on the bottom. Well, that negative can pull out front, and what we have is negative our original function. And that's an indication that it's symmetric over the origin. Okay, so here's our IKen statements again. That means we're at the end of the video. So after watching this video, after doing the practice, you need to be able to do all of these things. If you can't, maybe you need to watch the video again, maybe you need to ask some more questions. So that's it for today. I'll see you in class, and I'll see you online.